Hi, here we discuss about a project MACISH Approximate Multiplier for power efficiency in FPGA design using internal self-healing. Here, the Approximate Multiplier have become an important solution for modern digital signal processing, image processing, artificial intelligence, machine learning, multimedia and edge computing application, where a small loss in computational accuracy is acceptable in exchange for significant improvement in hardware efficiency. So these multipliers are often lower power consumption, reduced hardware utilization, shorter critical path delay and higher optimized speed compared to the accurate multiplier. However, the reduction in circuit complexity often increased computational error, which limits their adaptations and application, requiring a balanced trade-off between accuracy and hardware efficiency. Several recursive approximate multiplier architectures have been reported in literature, including FPGA-based internal self-healing design that primarily investigated selected 4-bit and 8-bit and recursive configurations. Nevertheless, the available work mainly focused on power optimized 8-bit implementation and does not comprehensively explore area optimized recursive configurations or demonstrate scalability towards higher bit width architectures. To address this limitation, this work designed and verify 5 approximate 2-bit multipliers, which means M1 to M5, and developed a recursive 4-bit multiplier architecture using table 3 and table 4 configuration. The best performing 4-bit designs are further employed to construct an optimized 8-bit recursive multiplier, followed by a comprehensive analysis of area optimized and power optimized architecture. As the major contributions of this work, the most efficient and lower error 8-bit multipliers are recursively utilized to develop a novel 16-bit approximate multiplier and demonstrating a scalability of the proposed methodology while maintaining improved hardware efficiency and computational accuracy. The proposed architectures are evaluated in terms of LUT utilization, power consumption, propagation delay, operating frequency, error metrics, and overall hardware efficiency. The functional verifications and performance analysis are carried out using Verilog HDL on the Xilinx ISE design environment targeting the Xilinx Vertex 5 FPGA, where the proposed recursive architectures demonstrate an improved balance between resource utilization, speed and power consumptions and approximate error. Now we can verify the paper. So this paper is fully designed for the approximate multiplier for power efficiency in internal self-healing method. So for this concept, they are used architecture with approximation stage and healing stage. It will be mentioned in figure 1. Internal self-healing based approximate computing methodology proposed in MACISH method. Okay, so here the input once you are given, it will be given to the approximation stage. Okay, so for that here they created a different number of approximate multipliers in 2-bit level. Okay, so 2-bit M1, 2-bit M2, M3, M4, M5. Okay, so using this M multipliers, they created a 4-bit multiplier, and that 4-bit multipliers, it's required a healing stage. Okay, so once the healing stage process completed, then it will produce the approximate output. For that healing stage method, they used a normal traditional method of 4x4 recursive multiplication using 2x2 multiplier method. Okay, so this is a method that will be handled. Okay, so here the multiplication process, it will be required for 4-bit multiplier AH into BH and AH into BL and AL into BH and AL into BL. Okay, so this process they will be completed, and after the shifting process they will add the value. Okay, for additions we have used 8-bit and 16-bit and ripple carry adder method. It will be used in this architecture. Okay, for logic reductions, we can possible to change the adder part and we can prove the number of comparisons. It will be possible in future cases. Okay, for this paper novelty, here we design a 16-bit novel approximate multiplier. Okay, so first of all we need to verify how they design a 4-bit multiplier. Okay, so using 4-bit multiplier, they are using M1, M2, M3, M4 and M5 architecture. Okay, so this is a reference architecture for the approximate multiplier. This all come with a 2-bit multiplier. Okay, so 2-bit means A0, B0, A0, A1, B1. Okay, so here this one, okay, A0, B0, A1, B1. So the output, it will become with a O0, O1, O2, O3. Actually 2-bit multiplier means it will become with a 2n size. The 4-bit output it will become. Okay, so here using this M1, M2, M3, M4, M5, here they given a table 3 configurations and table 4 configurations to construct a 4-bit multiplier. So this is a table 3. Okay, so here the 5421, 5421 means M5, M4, M2, M1. Okay, so that is a MSM to LSM. Okay, so which means MSB to LSB, the most significant multiplier to least significant multiplier. Okay, so here it will be take for LUT 14, 15, 15, 16 in the range, and the error it will be placed in the e power mention. Okay, so here the next part of the 4-bit multiplier, power optimized and recursive. So here they will be used R1311, 1315, 4335 and 1555. Okay, so this two set they are given already. Okay, so they mention, so this table 4 it will be more good compared to the table 3. Okay, so table 3 it will be helpful to reduce the number of logic cases. That's why it will be come with the LUT in less level 14, 15, 15, 16. But table 4 it will be helpful to prove the accuracy level. That's why it's a little increases compared to the table 3. So it will become for 16, 20, 21, 22. Okay, so here this part we also implemented. Okay, so this is a well-logical coding. This is a 2-bit multiplier. Okay, so we proved all the multipliers. So here M1, M2, M3, M4, M5 in models and simulation. Okay, so here can analyze the different range of input and different outputs M1 to M5, and error also we analyzes. Okay, so here error mostly it will be come in a M2 multiplier. Okay, so M1, M3, M4, M5 it's not come with a more error, but it will be come with a MSB error. Okay, so at the maximum size of 3 means it will become with the MSB error, but M5 it will be good. Okay, why? Because the M5 architectures they used as a normal multiplier, normal 2-bit multiplier means it will become with all the partial product A0, B0, A0, B1, A1, B0, A2, B0 and 2 full adders, sorry, 2 half adders it will be used for to reduce the partial product. Okay, so it's not approximate one, it's accurate one, that M5 multiplier. Okay, so using that M5 multiplier means here the table 3 the minimum number of M5s it will be used in here, but here it will be used maximum numbers. So M5 this here R1555, right? So this multipliers it will be very good for performance. Okay, so that's why it will become with a 0.00 error. Okay, so based upon this selection, okay, so here the MSB, LSB it will be splitted, right, as per the architecture of AL, AHBH, AHBL, ALBL and ALBL. The 4 multipliers it will be used. So any one of the multiplier we can give a accurate, and any one of the multiplier we can give approximate. That is a tested process happen here. Okay, so using this M1 to M5. Okay, so that is a design happen this 4-bit architecture also. So this is a 4-bit code. Okay, multiplier code. Here also we analyzes the error. Okay, so here you can check the 4-bit code. So in this 4-bit we tested all the table 3 and table 4. Okay, so this is a table 3 and this is a table 4 configurations. Okay, so here you can verify the analysis. Okay, so here the 5155 and it will be come with a very less error. Okay, compared to other multipliers. Okay, so next job is a 8-bit multiplier. Okay, so the 8-bit multiplier already they provided a table FPGA IS H1 H2 H3 H4 H5 in table 6. Okay, so they used 1311, 1311, 1311, 1315. Okay, so this is all the 4-bit multiplier. Using 4-bit multiplier, they developed a 8-bit multiplier configuration here. Okay, so from this we created a 8-bit multiplier. Okay, so here this is a 8-bit multiplier. So ISH1 to ISH10. Okay, so they completed 1, 2, 3, 4, 5 only. Using the same format, they used this part of the configurations only. Sorry, table 4 part configurations only. They created as a 8-bit multiplier. Why? Because this performance is compared to very good compared to table 3. But we have designed table 3 and table 4 also for 8-bit multiplications. That's why we given a ISH1 to ISH10. Okay, so here you can analyze the value, the maximum size of the value. Okay, so here you can analyze the original value. So original value is a data check is a 7198 here. Okay, so first 1, 2, 3, 4, 5 multipliers, it will become with a 7 series, and ISH1 only come with a 6558. But in the 6, 7, 8, 6 to 10, it will become with a 6 series. Okay, so it will become with a more number of errors. Okay, so here we analyzes the error rate also for each multiplier. So MED, NMED, MRED error rate, all the multipliers separately we analyzed it, so we can take it for comparisons purpose. Okay, and the next job using this 8-bit multiplications, we analyze the best performance multipliers, so ISH1 to 5, and then we created a 16-bit multiplier. So this is a multiplier code and the simulation result for 16-bit. Okay, so here you can analyze it. So A, B and product output. Here also you can analyze the error. Okay, so MED, NMED, MRED error rate. Okay, and we analyzes the different number of values. Okay, so we run this cycle up to 50 numbers. Okay, so every 50 numbers it will be updated the error values. Okay, and this code we have synthesized in Xilinx Vertex 5 FPGA. So this is a 8-bit multiplier architectures. Okay, so this one come with the overall multiplier. Okay, so M1 to M10 we integrated in a one approximate multiplier size. Okay, but in the code we can compare this one separately. So give a separate set of top model, and we analyzes the each multiplier logic cases of LUTs, slice registers, IOB, delay and power separately, and we put it on your table. Okay, so overall performance. Okay, so it will be analyzes in LUT equal to 404, and you can analyze the RTL schematic. Okay, so this is approximate multiplier. So here totally 10 multipliers we used. Okay, so approximate multiplier ISH1 2. Okay, so adder means it will come with a 16-bit adder. Okay, it's a ripple carry adder only. So R1315 means it will be come with a number of M1s. Okay, so M1 means it will be come with a base paper architecture. Okay, and the same procedure we have done with a 16-bit. Okay, so this is a 16-bit design. It will occupy the 446 of LUT sizes. Okay, so it's also same. It will be included all the multipliers. Okay, so this is the RTL schematic. So FPGA ISH5 442. Okay, so this series we have used it here. Okay, and this is a comparisons table. Okay, 2-bit multiplier, 4-bit multiplier, 8-bit multiplier and 16-bit multiplier sizes. And we have written abstract document for this project: title, base paper abstract, implement, proposed title, proposed abstract, disadvantages, advantages, proposed system. Okay, and related notes for this project with all the multipliers and Finally, we come up with a literature review and references. Thank you.
Are you planning to publish your next innovative research in IEEE transactions on VLSI 2025? Welcome to NXFE Innovation, where future-ready VLSI research projects are designed with novelty and quality for global researchers. At NXFE, we provide novelty-based VLSI projects carefully aligned with IEEE transactions on VLSI 2025. These projects are not yet published, offering you a clear opportunity for unique contributions in top-tier journals. Our research covers key domains like low-power VLSI design, analog integrated circuits, FPGA implementation, signal processing architectures, and emerging applications such as cryogenic front-end ASICs, physical unclonable functions, and self-recycling SRAM cells. Each project comes with a verified novelty, simulation results, and complete customization for your journal publication. You'll find practical design files, HDL codes, schematics, and step-by-step explanations to guide your research journey. We provide 100% accurate results and comparisons of source code with all results, basic documentation, and explanation video. We provide execution support with explanation-recorded video explanations on your system. IEEE guidance for paper writing and journal publication. Affordable project packages with ongoing support. Customization to match your research needs. Early bird offers and discounts for researchers. Don't miss the chance to publish in IEEE transactions on VLSI 2025. Visit our website today, explore our latest research projects, and get started on your journey to innovation. Join NXFE Innovation, shaping your future for VLSI research.